Okay, so we are looking at the dimer model on Z2, the interacting dimer model. So we are on Z2, and actually we are on a periodized, on a torus, and by a torus in Z2, and for those who were there, remember I've chosen some axis of coordinate frame, which is not the usual one, horizontal vertical, but tilted by 45. And the reason is that Z2 is bipartite, and it's convenient to keep track of that. So sort of the elementary cell in the lattice is like this one black, one white sides next to each other. So the next elementary cell is not here, but it's here, and then here, and so on. So it's natural to choose a coordinate frame where this would be the vector E1 and this would be E2. Okay, so this is my choice. So I'm periodizing the lattice in these two directions so that the torus will look like something. Alright, so this would be the torus TL. And then on this torus, I'm putting weights on the edges, and the weights respect this periodicity. So the weights will be, you have 4 types of edges, 2 horizontal, 2 vertical. I put weights T1, T2, T3, T4, but T4 I choose to be 1. I can rescale all the weights to be by a common factor. Right? So you have every edge has a type from 1 to 4. Okay, later, well, actually very soon, all the T's will be put to 1, but I want to keep them because the phenomenology is more interesting, and anyway, now we're working out a result for the general case of the weighted case. And then what I said, well, the non-interacting model will be the one where you have just, it's a measure, a probability measure on all perfect matchings of this lattice, so, or dimer configurations. So dimers cover all edges, all vertices, but exactly once. And the measure of the matching will be proportional to the product of edges in the matching of TE. And then, of course, you normalize the probability. This is non-interacting measure. What I said last time is that it has a limit when the size of the torus goes to infinity. It's now a measure on the matchings of the whole plane, and has very nice features. It's a determinantal measure. Correlations of involving finite number of edges are given as a n by n determinant, where n is the number of edges you are looking at. I wrote down a determinantal formula, which I will more or less recall next time. Later. And then I introduced the height function. Okay, if you want, I will reintroduce it. But there is a natural to every configuration when you are, let's say, in the infinite plane. To every perfect matching, you have associated a function defined on the faces, which is a multiple of 1/4. You can define to be an integer value. It's a bijection. Once you know the height, you know the dimers, and vice versa. And under this limit measure mu p t, the height function behaves like a Gaussian, a massless, log-correlated Gaussian field on the plane. Okay. This is true when the weights are all ones, but it's also true in a larger regions of values of t's. Okay, and
but not all values. Not all values.
Not all values. There is an open region of t which can be characterized, for which this is true, and this kind of statement was of the type that here I checked following David's question. So if you take it for a kind of statement, you can prove it. You take a test function phi, which is C infinity on R2, compact supported, and the integral of phi equals 0. This is actually important. And then you take epsilon squared, the sum over all faces in the graph in Z2 of the height at the face x times this test function at x times epsilon. So let's say computed at the center of a face and but smooth it out. And this stuff here converges in distribution under this measure p to a Gaussian, the center. Well, you have to subtract the mean. This Gaussian. Central Gaussian of variance integral phi of x, phi of y, g of x minus y, and I think I gave explicit what g is. Anyway, at short distances, this is 1 over 2 pi squared log of 1 over the distance. And
but that's with T all one or what?
this is for T all one, but in more general, it's true. Okay, so let me say two things. If you don't require average 0, then you have something that diverges like log of 1 over L, so times the average of phi. Okay, so this is important. The second thing is if T, well, what is the condition of T? Well, one object that will play an important role, also already last time, but also this time, is the propagator of the non-interacting model, which is defined as the integral on the torus on the two-dimensional torus minus pi squared of ps minus y of a certain function mu of p. I wrote down the function last time. It's a polynomial in e to the ip1, e to the ip2, and it involves the weights. So, okay, I don't have the formula here, but it was something like t1 plus I t2 e to the pi1 plus something of this type. Will reappear in 5 minutes.
So is little g and capital G have something to do with one another?
They have to do with one another, but they are not the same. It's just a misprint. But no, I will tell you in a second what they are.
Since I was not here
last
time, I missed your definition of H. The height function.
Okay, so I can redefine it. One way to do it is to say the following. At each white vertex, the height function, when you go around that vertex clockwise, the height function always changes by 1, except when you cross a dimer where it goes down by minus 3. So 0, 1, 2, 3, and then 0. And then at black vertices, you do the same thing but anti-clockwise. And actually, the definition I've taken, I've divided all heights by 1/4. So this is the height function. I didn't define it this way, but it's the same thing. And then what I'm saying, there is a certain thing which will play the role of a propagator for fermions, which is the Fourier coefficients of a function on the two-dimensional torus, where this mu of p is something explicit. I can write it down. But, it's a polynomial in I to the ip1, I to the ip2, involving the weights. Okay. So the thing I said last time is that if you take all weights to be 1, you check that mu p has 2 simple zeros. 0, 0, and pi, pi. And in general, all what I will say will be true for all the weights p, such that mu of p has 2 simple zeros. Okay, so this is the condition. Which since p mu is explicit, you can work out the region, but I will not. Okay. So now this g here is the following thing. Is related to this mu in the following way. That g of x, say, it is, if I shouldn't get it wrong, it's minus 1 over pi squared logarithm of absolute value of what I call phi plus of x, and phi plus of x is related to the behavior to the okay. So mu of p vanishes at 2 points. And the phi plus, we look at what is the gradient of mu at these two singularities, at these two zeros. So more precisely, I have it somewhere. Yes. Phi plus of x was beta plus, which is the derivative with respect to p2 of mu at 0, 0. Times x1 minus alpha plus times x2, where alpha plus, as you can imagine, is the derivative with respect to p2 at the 0. Okay. So this for x small, this is linear in x, so it's a singularity, it's log singularity of the covariance. But there is a very specific form, which involves the way how this mu vanishes at the singularities. Okay, so this is something I did last time, and no. So the other thing I did was to say, well, okay, now this is about the non-interacting model, which has been solved by Castellan 50 years ago or more. But we will be interested in the interacting model. Yes.
Just to check if I mean, if mu, the derivative of mu are computed in the zero, not in zero.
Yeah, okay, so this, sorry, yeah, so this in the case t equal 1, the 0 is at 0.
Okay.
In general, yeah, thanks. In general, you have to compute, yeah, thank you. In general, you have to compute it at a 0. So you have two zeros equal p plus and p minus, and you have to compute them at p plus and p minus.
You have to compute them at both places?
Yeah, so actually there exists a simple symmetry that
So it's the same.
one is something like they are related.
It doesn't matter which one you choose.
Yeah, it doesn't matter. Mu has a symmetry like mu star of p equals mu of p minus p or something like this.
Sorry, so I wasn't last time. Was it? So when you said t is equal to 1, you mean just all the weights on the edges are 1, right?
Again?
All the weights are 1.
Yeah, so it's just a uniform measure.
So uniform measure on all the configurations.
Yeah, but yeah. I mean, it's nice. It's richer. The model is richer if you look at it in terms of with this non-trivial weights t, because you can, for instance, fix a global tilt in the height function. But essentially, from now on, t will be almost always 1, because otherwise never get anywhere. But if you have other questions, so then I was introducing the interacting model. This is the last thing I did. When you're in the interacting model, you start again in finite volume. Possibly you have the weights if you want to put them to 1, and there is an interaction parameter lambda. So lambda is a real number. Later it will be small, but for the definition of the model it doesn't matter. And the probability of a configuration will be proportional to, if you have non-trivial weights, then you have the usual term. Then times exponential of lambda times some interaction that is not just factorized over the edges. Okay? So in this way it's very general, but we are thinking of interaction of the form. You take a local function of the Dahmer configuration and you sum it over all the box. So the two examples that I mentioned is W of m being the sum over all faces of the indicator that at the face f you have either this configuration or this configuration. So you have two parallel dimers as a face f. This is the one we worked out in the first work with Alessandro and Vieri. And the second example is the same thing, where you restrict the sum to be on the even faces. So even means just one of the two types, like those who have bottom right black vertex. Okay, and it's the same thing, but it's restricted, and then these even faces. And the point is that this second model is equivalent. It can be mapped into the 6-vertex model with a certain choice of parameters. So, and in particular, if you compute the parameter, the delta of the 6-vertex model, which tells you whether it's free-fermionic or not, this is something like e to the minus 1 to the. It's this way. So it's free-fermionic. So delta equals 0 only if there is no interaction. Otherwise, you're not free-fermionic. Okay. So these are two examples I gave. And for some computation, I will use this one because for some reason that you will see, it gives simpler. At some steps, it's a bit simpler, but they don't really make a huge difference.
Actually, first stupid question. The first 6-vertex model is an integral model. Is Max the solution of the 6-vertex model?
Like for the free energy and we don't. Yeah, okay. In this business, we don't really see the difference. It's just when I will want to represent the partition function of this model in terms of fermions, the expression that comes out is a bit simpler in this case, but then in the later when we apply all the method, you don't really see the difference. But yeah, you're right.
But you don't care whether you can take much more general ones that are not integrable.
Yeah, like this one.
Yeah.
Actually, in the first work we actually look at this one, which at that stage looked to us more. All right, so
in the model 2 have even faces.
even means in your lattice you divide faces into two sublattices like this. Say that these have black vertices here and the other two have white vertices in this one. One of the two sublattices, it doesn't matter which one.
Okay.
All right, this was last time. Okay, so let me, the plan for today would be to, first of all, tell you what we can prove, first thing, and then start sort of setting up the
Completely stupid question, since I wasn't here. So this model is motivated by what kind of questions? What do you want to do with it?
I think it appeared in the physics literature like this one. It's not incorrectly, really. Was it probably an effective model for quantum dimers? I think this is the way why it appeared initially. But for us, the motivation is not so much this one, is to see once you break the integrability, what survives of the Gaussian asymptotic description and of the like out of something I didn't mention. So correlation functions for this mode, for the non-interactive model, are decayed algebraically. What can we say once you have interaction? So this is our motivation, and somehow initially the goal was to do similar things to spin-spin correlation in non-integrable Ising models. In spirit, there are some of the results look like, this was a motivation.
So do you have any other conditions besides lambda being small and m being local? No symmetry condition you have to
No,
propose?
because as I mentioned last time, okay, in the long paper we do use symmetries, we do. But so now we're working out the case of the general case, and in the general case, meaning once you put the weights, already at the level of the non-interactive model, you have lost like rotation symmetry.
Yes.
Now we need translation symmetry, that's for sure. But translation symmetry.
I imagine.
Yeah.
Otherwise,
But the discrete rotations we don't need, because anyway, as I said, once you put the tilt, discrete rotation symmetry is already broken. So
no, I asked this question to Alessandro before, but I'm just worried when you add an interaction like that, whether you might be going off of massless theory.
no,
You stay.
yeah, just the poles, the singularities are shifted, and the values of alpha and beta are shifted, but just stay
That's
by
all.
massless. Okay. Any other?
So is lambda negative here?
Again, no, here, lambda is real. So that is
Does it matter? I mean, you can pick. You're saying you can pick both. So if lambda is positive, what does the general effect of this do? This is one going to a line. Basically?
okay. So what happens? So we will, in the end, all the result will be for lambda very small, and then it will not. If you allow lambda large, then things then the sign starts to matter. So for lambda sufficiently large, it's known that there will be columnar order. Things will be organized in there is longer range order. For lambda very large negative, actually I don't know whether anything happens. I think it's not proven. I think it's not known. I try to think of it a bit. Anyway, for large lambda, there are works by Hellman, Lee, okay, forgot the references. Who proved the ordering for large lambda?
Einman and Prescott.
Okay. Okay, so but this is known for. Okay. Okay. So the plan, as I said, would be now to give you some theorems, well, two theorems, and then start setting up the formalism. Right. So theorem one. So theorem one. Theorem 1 says, so Theorem 1 appeared in this work with Alessandro and Vieri in Situari Poincaré probability and statistics in it says the following. So, it is formulated for the case t identically equal to 1. And it requires lambda small. So don't ask me how small it is. I mean, it's always the same, so probably extremely small. Some certain series has to converge. So certainly we are far from the ordering translation. Okay. So, well, first thing which is not really present in this work, but is something we can prove now, is that there is no issue in proving that now the t will disappear forever in this theorem because t equal 1. Actually, these measures have a limit as going to infinity. So I put this point essentially to introduce the notation P lambda as the infinite volume measure of this measure, of this finite volume measure. So the important point is the following, that under this infinite volume measure, if you look at the dimer-dimer correlation, so you look at the indicator, there is a dimer at E and an edge E and a dimer at an edge I prime, and I subtract the product of the averages. And remember from last time, so E, I would say it's I will say that E is an edge of type R equal 1 up to 4. Remember, you have 4 type of edges. And it has a coordinate x in the sense that the black vertex of E has coordinate x. So E is identified once we give the coordinate of this black vertex and the type. And same thing when you have R prime, R x prime. Okay, so at large distances, when the two things are far away, this behaves like, certain things I will put in red because they differ from the non-interacting case. There is a prefactor depending on lambda over 2 pi squared. Then there is real part of, KR, I will recall you in a second what they were. T plus is exactly what was there before. It's essentially this linear function of x, not x minus 2 squared. Then, the KR, let me remind you right away. KR depends on the type of edge. It is 1 I minus 1 minus I. So if R is type 1, you have a 1 here, otherwise. So this is the first term. And then the second one, there is an oscillation. So every x is x1, x2, and similarly for x prime. X prime plus x2 minus x prime 1 plus x prime 2. So it's something that oscillates from plus minus according to the distance. Then there is a constant that doesn't really matter. It's an explicit constant over 4 pi squared. And then times, there is a prefactor depending on lambda, like here. And then there is a 1 over 3 plus x minus x prime absolute value squared. So it resembles a bit this one, but here you have absolute value, here you have real part. And then you have something of order 1 over distance to the power 2 plus something positive. So something became like 1 over distance squared, something, there is an important thing here I'm forgetting. There is a critical exponent no. And the red parts are the things that differ from the case of the non-interacting model. In the non-interacting model, we had 1 here, and we had 1 here. Otherwise, the structure, and this thing was also 1. Otherwise, the structure was exactly the same. Well, here we had 3. So this is the first statement about the two-point function. Let me mention that these kind of formulas already appear in a short work by Luigi Falco, I forgot which year, but 2 years ago. So, but I hope this is clear. So there are 2 parts. One became like in this precise way, like the 1 over the distance squared, and everything, all that changes with respect to the free case is prefactor. In the second one, instead, you have this nu which depends on lambda. And then you have an error factor. And all the functions of lambda that appears are analytic functions of lambda that equals 1 at lambda equals 0. So this is, I didn't write it down, but for small lambda, you have analytic functions such that this is true. There are similar formulas for multi-point dimer correlation that I will not write down. And then, okay, so maybe first the theorem one is more, no, okay, let's put together the other information is that if you look at, so the second information that actually is easy to derive from this and multi-point versions of this equation are that the height field again converges to a Gaussian, not correlated Gaussian field. So for instance, let me give a sub result. If you take the height function, height difference between two far away faces, let's say f and f prime, and divide by log of f minus f prime. This converges as f minus f prime get far away. So sorry, this is the variance. Right. So this converges to in the free case it was 1 over pi squared. Now it's 1 over pi squared by times this a of lambda. Exactly this thing. And as you can imagine, if well, it's not just constant, but it's part of the theorem that this random variable tends to a normal random variable with this h of f prime minus h of f divided by square root of the variance tends to n0. And there is a similar statement for in the terms of related field. So when you integrate, when you sum against the test function, etc., etc. So you see, okay. The point is that, so this is a computation I would like to show you how to go from here, at least to deduce the variance, because it's a very nice computation, but maybe I will leave it for the end of the lecture.
The convergence is when the distance goes to
yeah. But the thing you should notice that, so somehow it's only this term here that determines the variance, or the large scale behavior. This term here doesn't, so the b of lambda will not appear in the scaling limit. And the point is that there are these oscillatory terms. So I will try to convince you of this, of why this follows from this later.
Does it not appear because of the oscillation?
Yeah, that's exactly the thing. So when you compute height differences, you have to sum dimer indicators. And when you compute the variance, you have dimer covariances. And because of this oscillation, it's as if it behaves like as if it decayed more than 1 over 2 nu. Yeah. So that gives you a. I will sketch the computation now, but I will not give the details, and then if there is time,
so, can I ask? So the nu can be bigger than 1 or it can be less than 1.
Okay,
so
this was essentially the next comment. Yeah, the sign of the nu depends on. All right. So one thing we did check is to check whether this nu would be trivial or not. Now it could be trivially 1. So remark, it is not in general. It requires some work to work it out, even at first order. So once you know it's analytic, you can compute it order by order. So we did the first order. So remark. When the interaction, for instance, we did the computation for a specific interaction where this the one where you sum over all the faces. The interaction 1. The interaction 1, which is this one. For this one, we work out nu, and actually also a, and they turn out to be 1 minus. Okay, I give you the thing just to show you it's not trivial. 1 minus 4 lambda. Same thing for a plus order lambda squared. So you see, it's not non-trivially constant, and according to the sign of lambda, this exponent is larger or smaller than 1. At second order, we didn't compute it. Okay, so the first observation is that, okay, so you have a non-trivial critical exponent. The other thing is that we also did another first order computation to check, well, among other things, to check whether. Another observation is that this nu of lambda and a depends non-trivially on the weight t. If I put back the weights t, we have a similar theorem that will not state. It's similar. Now nu will, and a will also depend on the weights t. So remember that in the non-interactive, I just finished here. In the non-interacting model, the prefactor of the variance was just 1 over pi squared with no dependence on t. Once you put the interaction, the dependence on t is now is there.
So this t dependence only occurs if lambda is different from 0.
The what? Excuse me?
The t dependence is only observed when lambda is different from 0.
Yeah.
I see.
So
for lambda equal
nu
to
of
0.
lambda equals 0 is 1 whatever t is.
Okay.
Oh.
Your interaction is always that specific one, or is that a kind of relatively general?
Where?
Well, so, for example, that formula with the formula.
This formula is for this specific interaction. It will certainly be a different for now. So there is, it really depends on the t's and on interaction. So it's not a universal.
But this theorem is true for class of interaction somehow.
Yeah, so
these
there's
are just two examples.
Yes. So the first theorem is written really for this interaction because it was already known enough. So the one we are writing down now for the general T, we are also trying to formulate for more general. So we are formulating for more general interaction, just requiring finite ranges. So this was one remark that nu is not universal at all. But the thing that is already suggested by this first order computation is that okay, there is actually theorem 2. Which says that the equality nu of lambda equals a of lambda is true, not just at first order, it's just true. And well, again, whenever they exist, so for lambda small, when these functions exist analytic, then they are the same. So the prefactor here, which ends up being the amplitude of the Gaussian field, and its critical exponent are just the same number. Both depend on trivially on t, on the interaction and so on, but the quality is.
This is for the other model, the 6 vertex? Which model is theorem 2 for?
Oh, okay, so presently it's written, so presently the published version is a JSTAT with also with Vieri and Alessandro, and it's formulated for t equal 1, okay, the same model for which we did the first papers. But in the work in progress, so t equal 1 and model 1. But in the work in progress, it will be also for t whatever and yeah, other more general interactions. But if you want something that is written down, it's written down in the symmetric case. But if you believe me, it's also general.
What is JSTAT?
JSTAT is General Statistical Mechanics Theory and Experiment.
Statistical physics.
No.
Mechanics.
Statistical Mechanics.
The online journal.
Yeah. Published in Trieste. Okay. These are the two theorems. So as I said, I'll give precise statement, especially in the case which is already written down, but believe me, it's true more general. Yeah.
Is this the Haldane relation?
Yeah, exactly. So for those who know, so this is at least the analog of so-called Haldane relations for Latinger liquids. So it's really okay. Let's see. Who wants to see briefly why this implies this, or should I go on with setting up the formulas? Why the? I can either explain briefly why this thing implies the logarithmic variance, the logarithmic Prof of variance, or I can leave that for the end of the lecture.
You decide.
Okay, let's leave it for later because it's kind of live computation and
Whichever is pedagogically better.
Mm-hmm.
I don't know. No, it's a nice computation, just that it will avoid doing somehow harder things.
With a lambda, there's a minus sign.
Again?
It depends, it's 1 minus 4
Yeah.
pi lambda. So the wave that you chose, it's sort of encouraging alignment, right? With lambda is positive.
Okay, so it is encouraging aligning, so it should be encouraging order.
Yeah.
So hopefully, yeah, the exponent is smaller, so it decays slower when lambda is positive.
So then the 2-point function seems to be getting smaller.
So this, no, but I think you should rather look at this. I mean, when nu is smaller than 1, this term is dominant. Because this one is 1 over square, this one is 1 over something small. So in fact, you have. Now the staggering here is because there are a lot of constraints when you put the dimer somewhere. But this becomes dominant and it's slower when lambda is positive.
So when you, I don't want to distract, but when you go to a fermion representation, will that be a Fermi surface effect, this -1?
Okay, I will get there, but it's related to the -1 is related to the fact that one singularity is at pi, and then you get when you take the propagator and expand it close to that singularity, you get the factor e to the I x minus y pi, which gives you exactly this. I don't know if it answers, but in fact, the fact that one of the two singularities is one of them is at 0, one of them is okay, but that should be come out.
I guess you still don't, can you compute monomer correlations to it?
No. Already for the non-interacting model, I cannot say I understand how the okay that works by like Dubeda. I cannot say I can control that. So it's difficult.
It's hard.
Yeah. So I think there are. Well, if you wanted to do it for the interacting model, we are breaking translation invariance. So okay, we cannot do it for the moment. Okay. Let me leave this thing for the end of the talk. So the plan would be now to set a bit the ground for the methods we use. So the goal would be to arrive at the end of today, maybe to be able to show you how to represent the partition function and correlation functions of the interacting, and particularly also the non-interacting model as an integral of Grassmann integral. So I will start with a very brief reminder of Castellan theory. So I mean really the essentials. So Castellan theory. It's a really beautiful theory. If you have not seen it before, or even if you've seen it before. So suppose G now is a subset of Z2, which is bipartite. Well, it's bipartite of course, but suppose it admits perfect matching. For instance, it's I don't know, something like a 2n by 2n rectangle or something. It's a planar subset. It's a subset of Z2. And suppose you want to count the perfect matchings, or more generally to compute the partition function of the non-interacting model. Maybe I put back the weights here. There is no harm. So the point is that the observation by Castellan and Fischer was that you can compute this by just taking the determinant of a matrix. The determinant of a certain matrix, and the matrix is very simple to define. It's essentially just defined last time. So the matrix has rows indexed by black sides and columns by white sides. And these matrix elements are 0 if B and W are not neighbors. And then if they are neighbors, then the values are what I just called K1, K2, K3, K4. So let me just draw a picture. So, well, if your two things are like this, you get K2, which was IT2. If they are like this, you have K1, which was T1, and then you have, here you have D3 minus D3, which I called A3, and here you have K4, which was minus I. Okay, so you have, sorry, I made it, yeah. Okay, so it's like a weighted adjacency matrix, except that it comes with certain things that are multiplied by signs or by i's and minus i's. Okay, so I hope the definition is clear. It's a finite matrix, and the point is that the z is exactly the absolute value of the determinant. It's once you know it, it's kind of easy to prove. Well, first thing, okay, let me comment. Why the absolute value? Well, this really depends on how you label the sides. If you relabel sides, you are just exchanging lines of the matrix, so the value here will change. So you need to take an absolute value to hope the result is true. So the way to prove the theorem, I will not do it, but you just expand the determinant in permutations. You will see that all non-zero permutations correspond to perfect matchings. They have the right weights. They have you get the product of the weights. And you just have to check that the i's and the minus ones combine with the signature of the permutation in such a way that all the terms have the same sign, are multiplied by 1, say. And then you just get the sum of the weights. And so the i's and minus 1 are chosen so that this works.
So there's something clever about the choice of the signs. Now, when you work on a torus and it's not planar, what happens?
Yeah, this was exactly the thing I was going to say in a second. But there is a similar formula, but slightly more annoying. So let me give it away right away. So I will tell you what happens on the torus, and then immediately tell you that we will pretend we're not on the torus because otherwise we'll have. Warning on the torus. The formula needs to be modified. Modification needed. I mean, if you try to do the same thing on the torus, expand the determinant, you will check that unfortunately not all configurations are counted with the same sign. Some of them are counted with plus, some with minus.
It's because of the loops, right?
Yeah. So I will just tell you what is the recipe to fix that. I will not explain why, but again, once you know it, it's not hard to check. The thing you have to do is, now you have your torus. Right? So you have your Castellan matrix K. You have to define 3 other Castellan matrices simply by saying the following. You will define matrices indexed by theta 1, theta 2, both takes values either in 0 or 1. K00 would be the original Castellan matrix. And now the K theta 1, theta 2 is just obtained as follows. So remember, this is direction 1, this is direction 2. So what you do is multiply all matrix elements corresponding to edges crossing the torus, crossing the torus in direction 1 by minus 1 to the theta 1, and in direction 2 by minus 1 to the theta 2. So you are sort of just modifying the matrix elements. So you are putting sort of periodic or antiperiodic boundary. You are multiplying the matrix element corresponding to edges which go out of the torus in direction 2 by minus 1 to the theta 2, and same thing in direction 1. So if thetas are 0, you are doing nothing, otherwise you are doing something. Okay, and once you have done that, there is a theorem also proved by Castellan, which tells you that the partition function on the torus of size L with the weights is given by the sum by 1/2, a combination of these 3 determinants with certain signs in front, theta 1, theta 2. Let me not write down what the signs are, but the point is that there are 3 of them which has a sign, like 3 plus and 1 minus, or the other way around. It depends really on the parity of L and a lot of stuff, but you always have this structure. 3 of them minus the 4th, or 1 minus the other. So this is an identity which generalizes this simpler statement. And see, these matrices are almost the same, they just differ on the boundary. So,
Is there an absolute value somewhere?
no, it's
all
taken
in
into
the
account
seeds.
by this C. So, yeah. Okay, so this is first thing. Okay, one observation is once you know, for instance, take a planar case. Suppose you know that the z is the determinant of k. When you want to compute dimer-dimer correlations, it's enough to take derivatives of log z with respect to the weights. So once you know that, you can recover the determinantal formula I had in the last lecture. So once you have this, I mean, it's not hard to by linear algebra to compute all possible edge correlations in terms of the inverse matrices. Okay, so this was one first short reminder of Castellan theory. So I sort of warn you that on the torus you have to keep into account these 4 determinants, but immediately afterward I will tell you, for the purpose of the mini-course, I will forget this fact, which is a bit annoying. I mean, you have to keep track of it, and it's a bit annoying, but for the purpose of the lectures, let's forget it. So I will pretend that the partition function is given by just a single determinant. Okay, so I will, it's like cheating, but okay. So I will pretend that what? I will pretend that z on the torus is just given by the determinant of, say, k11. 1 is the antiperiodic. It has a nice feature, as you will see, that it is invertible, this matrix. It is for the square lattice with all 1 weights. Wait, okay, let me put not all 1 weight. This matrix here with the θ1, θ2 equal 1 is invertible. We will see in a second. And for instance, if you take the original 1 k00, it's not invertible. And then okay, so but anyway, I'm pretending this is the case. I'm forgetting the sum of the 4 to simplify the formulas.
So the other one is not invertible.
Again?
The other 3 are not.
K00 is not. The other 2.
Isn't that going to give it 0 then? If it's not invertible, then you'll get it down to 0.
Again. No, as I said, each of them doesn't count the configuration. It counts them with signs. So it may happen that they cancel. But okay, the sum of the 4, of course, this combination does not vanish, of course, it's a number, it's a positive number. But some of these determinants could be 0. In particular, it's easy to see that k00 is always 0. Okay, but let's see, I mean, k1, okay, take one k11 or k, for the others would be true. This matrix K are translation invariant matrices on the torus. So you can diagonalize them immediately in Fourier basis. Okay, so K, remember, is a function from black to white vertices. So if I multiply by a function on white vertices, which is just a certain function fp. So fp, what is that? Fp computed at the white vertex of coordinate x is just, well, the plane wave 1 over L p to the minus I p comma x, and I take a momentum p to be of the form p1, p2 of the form, so pi is 2 pi over L times an integer and I plus 1. Okay, so take a p of this form and I from 0 to L minus 1. Take p of this form, half integers, times 2 pi over L. Take this thing here, multiply by the matrix, and then it's immediately to check that, I mean, this is an eigenfunction, just because it's a plane wave, and the 1/2 keeps into account that, takes into account the boundary condition. So there is a little check to be done, but it's sort of trivial. So this function here is an eigenfunction. So I mean, it gives you fp computed at the black vertex with the same coordinate as x. No, sorry, I'm saying something. It gives you fp of the same function itself times a free factor times an eigenvalue, and this eigenvalue is exactly what I called mu of p before. Okay, So the mu of p which appeared in the propagator is just the eigenvalue of this matrix here. Okay, so this is something easy to check. You have this transition invariant matrix, you diagonalize in Fourier basis, and these are the eigen. Okay, so then once you have that, you can also invert the matrix. Oh, and by the way, if we were looking at K00 instead, I wouldn't have this 1/1/2. Yes. So in particular, there would be the eigenvalue when p equals 0, 0, and that would be 0 because you remember mu has a 0 at 0, 0. So the matrix K00 would have a 0 eigenvalue, so it's not invertible. But all the others, basically K11 does not.
So the determinant should vanish.
Yeah, so for K1, so for K00 it vanishes.
Yeah.
K11.
And should I understand why is K symmetric? Or why are all the eigenvalues real?
They are not real. But
But
they are related. For each one there is a complex conjugate. So once you sum the logs, so you get something real. Or even even when you take the product, sorry, they come in pairs, complex conjugates. So you get something real. Okay, so in the end, what happens is that, well, of course, the determinant is just a product of eigenvalues. For instance, from this, you can immediately, it's very easy to check. Well, okay, there is some little work to be done. That the free energy, so 1 over L squared log partition function, letting L go to infinity, converges to something that is just dp of 2 pi squared log of this mu of p. This is something that...
Why do they even come in pairs? Because the entries are not even real.
So there is mu of, you have the symmetry that mu star of p equals mu of pt minus p.
Is there any symmetry of the matrix from which you can read it off, or is it just magic?
I mean, okay. I think I don't have a good answer. One thing I can answer is that here I've made this choice with -1s, i's, and so on. There is always, you could always make choices where it just involve plus minuses, +1s and -1s.
Okay, then it's all.
Then mu has just
yeah, and then it has to come in.
when you make the i's, it's kind of the symmetry looks more exotic, but it's always possible to choose just +1s and -1s. F of t is the limit, the free energy. I wanted just to mention that that from this you get immediately almost immediately. You have to make sure that somehow these determinants don't cancel each other, but there is an argument to deduce this. Okay, so this was one thing, and then of course once you know the eigenvalues, you can also invert the matrix. So k minus 1 of between a white vertex of coordinate x and a black vertex of coordinate y, which I will also call g of x, y, is, well, what you can expect, is 1 over L squared, sum over p in this, p belongs to this domain, to this set here, of, well, what you expect, p x minus y, over mu of p, and, okay, here it's a bit slightly delicate if you want to do it properly, because this function can get very large close to the poles, but okay, if you ignore this fact, here you just see the Riemann approximation of the integral that appeared before. So, okay. So this is okay. This is organized everything. So now, as I said, with Castellan theory, you can compute for the non-interactive model in principle whatever correlation you like. Of course, you have to be able to diagonalize, well, if you're on the torus, this I've already inverted. If you're on a strange domain, in general, it's hard to invert the matrix K, of course. And in fact, I mean, there are non-trivial phenomena like limit shapes and so on, which are, I mean, show you that in general it cannot be an easy task. But on the torus, it's easy. You have it? Okay. So now the next point is to do something that, at the level of the free model of the non-interactive model, is kind of purely a static thing. Is to rewrite Castellan theory in terms of fermionic language. Okay? For the free model, this is not really needed, but for the interactive model, it's very complicated. So probably some people are extremely familiar with Gaussian variables. Some people are probably totally unfamiliar. I can assume.
We have had a course here.
Ah, okay. So everyone is familiar. Okay. Yes. Well, let me. My plan would be to remind the basics and. For those who are not familiar, so those who are familiar, try not to get bored, and those who are not, try not to get scared. So the point is that so let me write down first, in a sloppy way, what we want to do. We have our lattice with black and white sides. We want to associate to each black side. This is the black side of coordinate x. We want to associate a certain Gaussian variable p plus of x. And to the white side of coordinate x, this is a white coordinate x, we want to associate another Gaussian variable with the same coordinate but with a different index. So in the index plus minus, we just distinguish between black and white sides. It's convenient to keep track of this bipartite nature. So the only thing I want to define in the end are integrals of Gaussian variables. So we will have a family c plus x, c minus x, with x indexed by this torus, by our box. And now I want to give a meaning to things like deep C, a function of this function, of this variable. So I will take a pragmatic approach. And so the point is, this is sort of it is a symbol. I want to associate to a function, a number, which can be a complex number, and it has some properties of integrals, like it will be a linear map. And well, there are a few properties in common with integrals, but you should not interpret this as a measure, or you don't want to do Cauchy-Schwarz or things like that. Okay, so the prescription is very easy. First of all, I will define it only for polynomials. And since this application is linear, let's just look at monomials. So I want to define what is the integral of a monomial of the C. So I have a product of, I don't know, C plus x1, I don't know, C minus x2, blah, blah. It's a monomial. And the order by which I write the monomial method. So they are order monomials. Okay, so how do I do that? Well, the rule is the following. I fix an ordering of the variables. For instance, I state, for instance, that the integral of the product of all the sides of c plus x, psi minus, let's see if this is a convention. This is my convention. This particular monomial has integral 1, when all the variable appears in this order. Remark that it doesn't matter how I order the x, because, okay, you cannot remark it yet. But so the second rule is the following, that whenever you exchange two variables, when you exchange two of the variables, you change sign. So if one monomial is obtained by the other from exchanging two variables, the result will be minus the same thing. This is the second rule. Immediately implies that if two variables appear, I mean, if one variable appears at least twice, then the result must be 0.
That's whenever you change two adjacent variables.
Yeah, but even if you, let me see, if there are this, I think tap twice, and then once, I think well, anyway, I can also define it just for adjacent transposition, but I think once you do it n times, the other one n minus 1 times. Yeah. All right, so change the sign when you interchange two variables. And the last thing I have to say is that whenever any one of them is missing, if any variable is missing, It's 0. So in the end, it's just defined by giving the integral of one single monomial, and then you can, by applying this rule, you can, now you know what is the integral of any polynomial of the variables. And the next thing, sometimes I will integrate functions which are not polynomials. For instance, suppose I want to integrate something like e to the c1, c2, because there are two variables. So by definition, when you have a function like this, or an analytic function in general, you just write down the Taylor expansion, and you realize that at some point, some variables will be repeated. Like here, it will be repeated as soon as you take the second order. In other cases, you have to go to higher orders. And so by definition, I just truncate the expansion once things start to repeat, and then I apply the rule. So in this case, it would be just, suppose I have just two of them, this gives 0 and this gives. So the rule is when you have an analytic function of this variable, you just write down formally the Taylor series, and you put zeros to all monomials which have more than 2 repeated things. Okay, so hopefully, so these are a set of rules that will be enough to define all the integrals that will appear on the blackboard. Things can be defined in a more abstract way by exterior algebra, but I'm not familiar anyway with that. So as I said, I will just need this pragmatic point of view. Okay, so once you accept these rules, there are a certain number of algebraic identities you can derive. I will not derive them, but give a few of them that you can check, at least in the easy cases. Let me give a few consequences. Probably, certainly you have seen them in the course, or you know them already, or maybe not, so let me give them anyway. The first consequence, which is the one why I'm introducing them, is that you can rewrite the determinant of a matrix as a Grassmann integral. So idents or facts. If you have a matrix, A is an n by n matrix, and then you can write its determinant in the following way. Let's see. So where here the ordering convention should be that as before, that the product. So here you have you have an n by n matrix. You introduce n variable, n Grassmann variable with index plus and n with index minus, and the ordering convention is that the product, the integral of the product from 1 to n of c, the same as there. Once I fix this, everything is known. Now this is an identity you can check. You just expand this thing, and then you get the detail. It's an exercise. I think I didn't get it wrong with the signs.
Well, now suppose I only have 1 point. I mean, I know you don't want to allow that, but...
Again, sorry?
Well, if I only have 1 point, are you summing over...
Yeah, it's correct.
So if n equal 1, you get e to the minus a c plus x.
So you're not anymore insisting that the pluses are the black and the minuses.
No, here, here sorry, I have an n by n matrix,
Yeah.
n even or odd, doesn't matter. I introduce n variables sigma plus, phi plus, and n variables c minus.
That's okay, yeah.
But they're not indexed by black and white.
Yeah.
No, here it's a general. I will apply it later but here. So for just one variable c, hopefully, yes, for just one variable you write this is minus psi minus, this disappears, and the minus is because you have to interchange to get 1. Okay, so for 1 by 1 variable, the matrix is true, and it's true also for n. And by the way, so just as a comment, it's similar to the usual Gaussian fact that the determinant of a positive matrix, square root of the determinant of a positive matrix sigma is equal to the is similar in spirit, except that here you need to have sigma positive definitely invertible. But here A can be anything. Okay, but I should remind you of this. Okay, this is why such integrals will be called, for aesthetic reason or for obvious reason, will be called Gaussian integrals by analogy. So this is the first fact you can check. The second one, oh, okay. So in particular, okay, that will be around the consequence later. The second fact is that you can write now if you have an n by n matrix that this time is invertible, the matrix element xy of the inverse can be written as deep C e to the minus, okay, this stuff here, let me write it symbolically as C plus scalar product A C, not in the obvious matrix notation, just to shorten the thing. C minus x C plus y over also here is something, here of course you require A to be invertible because here this gives you the determinants when you want it to be non-zero. And again it's an analog of the usual Gaussian formula where when you put here xy, xj, you get the covariance between xj, xy, xj. Similar to Gaussian, similar to formula, Gaussian formula for covariance. Maybe for today, we just need to these two facts. No, well, of course I need also the big rule, the big theorem. Okay, the third fact is the big rule, so the fermionic big rule. That is also analog to the big theorem for Gaussian families. So let me say that, so let me denote, I have to choose a notation. Okay, so suppose that this matrix here we call G because it will be called a propagator later. So suppose I give you now a following notation that the expectation we expect the Gaussian expectation with respect to this with this. Let me give you the definition. So I want to define the expectation of some polynomial of the Gaussian variables with index G. What does it mean? It's just you take deep C e to the minus C plus G minus 1 C minus F. It's sort of the Gaussian measure. If you forget okay, so it's just I'm just defining what is this. So in particular, this stuff here will be the E A minus 1 of C minus 2 plus. Just a definition of what is there. And then the big call tells you, maybe I take another blackboard. Well, now when you want to take the average of a product, let's say C, okay, C minus x1, C plus y1, blah blah blah, C minus xn, C plus yn. I have to have as many variables with minus as many with plus, otherwise it gives me 0, and when they are the same number, it gives me the determinant of an n by n matrix. Where gn of x, y, coordinate ij is just g of xi. Okay, I hope I got them right. So the point is that when you have expectation with respect to this measure, this Gaussian measure I define here, of a product of many variables, you can expand it as a sum over all possible pairings, like this one. But they come with a sign, which is kept into account from the signature of the detail. Okay, so anyway, this is. I hope the recipe is clear. So this is.
No, I'm not quite sure.
Yeah.
But it's the determinant of what though? I mean, are
you take the n by n matrix. Sorry. Yeah. So,
you have to say that.
okay. So this is the n by n matrix.
Yeah.
Gn is well. Sorry. No. I think it was already correct. Almost correct.
No, I don't quite understand what you did, so that's why I'm asking.
Correct. You just want those parentheses on the right-hand side.
Yeah. So yeah.
You just want them on whether you just define your matrix to be and the matrix elements are G, X, I, Y, J.
Yeah.
Yeah.
Yeah, I think this is correct. But the matrix depends on all the coordinates. When I take I and J, it just depends on those two values. Maybe it's not terribly good. Okay. So what's the relation with what's the relation with So what do I get for the dimer model? So for the dimer model, remember the Z is the, forgetting the combination of the four determinants, it's just the determinant of the Castellan matrix, the index 1, 1. And then, well, by applying the first thing, you can just write it as integral dc of exponential of a certain thing that is called action. It's a bilinear form in the field. And this S is just, so C is just, well, it's just minus the Castellan matrix taken that. So it's just, if you want it, it's just sum over xy of k 1, 1 xy. The 1, 1 probably will be forgotten very soon. Phi x plus c minus 1. Okay, so it's a triviality. And the point which were, let's see if I can get there. So, okay, let's try to do what I want originally to do, which means I will not do the computation for the variance. But I think it makes more sense at this stage to do this. Okay, so for the non-interactive model, it's another way of writing the determinant. For the interactive model, it is not such an empty statement. So, okay, so the thing I want to do now is to convince you, actually prove it, that the partition function of the interactive model can also be expressed as a Grassmann integral, except that the exponent here will not anymore be quadratic in the C's, but will be higher order. So it will be sort of non-Gaussian integral. This is the goal of what I want to do now. Is it clear what I did so far? It's kind of quick. So let me write down the proposition. And here, for this particular proposition, it's convenient, but simply for notational reasons, to do it for the 6-vertex model. For the other models, it's a bit more heavy, but nothing conceptually. Proposition. When the interaction potential is just the sum over the even faces of these two indicators, then the partition function z lambda. Okay, z in our box with the interaction parameter lambda is equal to, okay, you have a sum over configurations. Okay, for some reason in these formulas I'm keeping the okay, so sorry, I just need to add something here, sorry. Okay, so this is for the partition function, but I can get something extremely similar if I want the following generating functional. So suppose I define the following thing, always for the non-interacting models. I take the following thing. Instead of taking the partition function, I sum over all the configuration, the weight of the configuration, and then times e to the sum over all edges of a certain variable, this is a real variable, AE times the indicator function you have an edge at E. Okay? You have a, dimer at E. So this is something that is useful when, if you know this stuff, you can get any dimer correlation by taking derivatives of this. If you take derivative with respect to the parameter E1A, E1, E2, you get correlations between the indicator function at E1 and E2. So this will be called the generating function of dimer correlation. Then nothing exotic is happening. I'm just multiplying the weight TE by TE times E to the AE. Okay, so it is an immediate consequence that this generating function is just given by dx e to the minus sum over all the edges of TE exponential of AE times either like this, the matrix element of the Gaussian matrix of the edge E. So I hope it is clear. So it's K of BW, well, BW on the endpoints of E times C plus E. E is the black at X and white at Y. Exactly the same formula as before, except that now the weights on the graph are not TE anymore, are TE times these prefactors. Okay, so it's the same thing. But it's useful to have this in a second. All right. So, okay, so copy.
What is AE?
AE are, so AE is a collection for each edge. I have a real variable. I will just use them to take derivatives and then set all a's to 0. They're real variable. Right. So the statement here is that the partition function is okay. So the partition function is okay. I was just recalling you what the definition. Then the statement is just a definition of partition function, and then the statement is that this equals integral dx of e to the SA of c. SA of c is all this stuff here. SA of c, also the quadratic part in c, plus alpha. Alpha is e to the lambda minus 1. So for lambda small is essentially lambda, times a sum over gamma. We'll tell you in a second what is gamma. Product of E in gamma of E gamma. So I have a few things to tell you what they are. Alpha, I told you. Gamma are all pairs of parallel edges at even phases. So they are this one. So for each even phase, you have gamma can be either this collection of two edges or the other one. Okay, so for each collection of these two things, I'm taking the product of the two edges which belong to E, to gamma, and E gamma is gamma equals E1, E2, no, sorry, EE, sorry.
Yeah, no, exactly.
EE is just the matrix element minus, no, plus the matrix element of the Gaussian matrix K of E times C, so it's this stuff here. If E equals the usual. I could have defined EE here.
Some chaotic interaction.
Yeah. The special thing of this interaction here is that it is exactly positive. When you take more different, more general interaction terms, like you sum over all phases, not just even, you get also 6. So, as you was mentioned, so here you have just a product of 4 fields C, because each E contains 2. So you have a psi psi and another psi psi. So it's a 4-body potential. For other interactions, like if the sum is done over all phases, you also have 6 term, 8, and so on. This is what makes the proof as a bit more awkward, but nothing more. Okay, so I still have 5 minutes. I can hopefully convince you of the proof because it's really easy. This is not hard
because
point.
these guys overlap. If you have, is that why you're getting higher powers? I mean, do you really get all higher powers, or just?
Well, so you mean for other interactions?
Yeah, for the first model, where you.
Because what you can have is just 2 plaquettes next to each other where you get this and then you can form strings. In fact, in that case, you have just a sum over strings of parallel things. And here in front, you have gamma alpha to the power cardinality minus 1, and then you have the product of the E. So it's very good. Yeah, it's the case. Okay, but let me.
So this is, you said this has just 4 fermions in the particular interaction?
Yeah. So this is the only reason why here I'm giving the proof in this case, because it's simple. Yeah. But as I was saying, okay, let me prove it. Maybe I will go a couple of minutes over time and more, hopefully. But this is a very soft fact. I mean, you will see it's a few lines. This is not the heart of it. It's sort of the beginning. Because then what you have is an integral which has a quadratic part and then a higher moment, and then what is like a perturbation, if alpha is small, of a sort of Gaussian integral, and then the work starts. So let me sketch the proof, or maybe you can give it.
I guess you're missing e to the a also in the interaction.
Yeah, no, here so here I'm giving it for the partition function. In fact, what you could do is, since there is a question, you can also.
Since you wrote SA, I thought you.
Oh, yes, sorry. No, sir, you're right. I have to take A equals 0. There is no A in the left hand side. But in fact, you could do the same thing for the generating function of the interacting model, where here I also add the plus A blah blah. And then there will be very similar things where here you have SA, and here each AE is multiplied by. Okay, so the only thing that changes is that S0 of C becomes SA of C, and AE is multiplied by E to the AE times. Sorry, that's it.
This, maybe it's not so good to have a K of E, because K is the Castellane matrix. You want something else, right? In the
Where? Here, in fact, it is the element of the Castellane. KE is if E is this edge here, it's just. Okay, yeah, sorry. Anyway, thanks for asking. It's just a compact notation for the matrix element between the endpoint, the black and the white endpoint of E. So for each edge, I take the corresponding custom matrix element, and I multiply by the 2 fields which are the endpoints. And of course, there is Y here, and then it should be correct.
What about S naught?
No, an A.
S naught means S where A is equal to 0. Because in this statement there is no A. Okay, so there should be no A here. Maybe I called it earlier just S. Sorry, I'm not very consistent. So if you are interested in the partition function of the interacting model, then this is the result. There is no A on the left, no A on the right. If you are interested on the generating function of the interacting model, where here you would also have the sum, etc., the right-hand side should also contain A, and the way it contains is that S should be replaced by SA, which is defined here, and that each time here you get the EE, you replace it by EE times E to the A. Other questions?
S of psi has a K, has a Gaussian matrix in it.
S is yeah.
Yeah,
So let me.
The
S is exactly.
It's a free one, it's the free one.
S is exactly minus C plus K C.
Okay, okay,
It's a free action.
okay. Okay.
Okay, let me see if it makes sense to. But it's one page, so if you resist, I would give the proof. Or
Let's do it next time, maybe.
oh,
Yeah,
It's good to review
it's
some.
just quite.
Okay.
Next time.
it's fine for me. Okay, so I will stop there.
Okay.